All right, next we're going to be looking at linear inequalities and graphing linear inequalities, and we'll start with an introduction and do a couple solved examples. So our goal when we're solving a linear inequality problem, and to be clear, these are linear inequalities in two variables, so with an x and a y. We're trying to represent that two-variable linear inequality on a graph. So often the solution to one of these problems is a graph, not a particular number, but an actual graph. So let's take you through the steps, and then I'll show you how you can test to see if some numbers work out, and then we'll actually do a couple real examples. So first we want to pretend that it's a regular equation, a regular equality with an equal sign. And we graph that line with either a solid or a dashed line, and I'll tell you how to know which is which in a second. And then we pick a side to shade by plugging in a point to test. And the origin 0, 0 is the easiest point to test. So just to be clear, our result is going to be something, I'll just draw an arbitrary linear inequality right here. We might have a line, it might be dashed, it might be solid, and then we will be shading on one side of the line. And so what that means is all of these points in this shaded region are solutions to the inequality. Okay, so we'll have an infinite number of solutions. Our solution set is a half plane. Okay. First, I want to just check to see, as a little practice, let's check to see if the following ordered pairs are solutions of the linear inequality. Y is less than 2x plus 5. So first I'm just going to plug things in with a little question mark over my inequality symbol, and then we'll see how we'll see how things work out. Is 10 less than 2 times 3 plus 5? Is 4 less than 2 times 0 plus 5? Is 1 less than 2 times negative 2 plus 5? And lastly, is 20 less than 2 times 7 plus 5. So some of these are going to check out, some of them are not, and we're just practicing plugging in numbers and seeing if they do check out. So is 10 less than 11? It is. That one checks out. So this one's good. That ordered pair works. And next is 4 less than 5. Yep, that one works as well. So we can check that guy off. That's a good one. Is 1 less than 1? No, it's not. 1 is equal to 1. So that one does not check out. That one doesn't work. And is 20 less than 19? No, it's not, clearly. So that one also doesn't work out. Okay, so we're going to be doing this a bit, just plugging in numbers to check to see if the inequality is valid or invalid. And so some of these are not valid inequalities, and so we want to make sure we just know how to do that. So let's do an actual graph. And the rules here are, if you're dealing with an inequality that has an equality as part of it, so less than or equal to or greater than or equal to, you'll do a solid line. Otherwise, you'll do a dashed line. So this is telling us that we'll do a solid line right here. Okay, so we're just first going to just graph y is equal to 2x minus 3 with a solid line. So let's go ahead and do that. Y-intercept of negative 3 and a slope of 2 up 2 over 1. And we can go in the other direction as well. Let's draw a nice solid line there. And I'm going to get mine to try to fit there a little better. Okay, cool. And now we have the edge, we have the boundary of our inequality graphed. We need to pick a side to shade. The easiest point to always pick is that 0, 0 point, the origin. And so let's plug in 0, 0. Let's see if 0, 0 works. Is 0 greater than or equal to 2 times 0 minus 3? Is 0 greater than or equal to negative 3? Yes, it is. So that means this point, the point 0, 0, is a part of our solution set. And then we can, let's see, we can shade in our solution right there. Okay? You don't have to be perfect with your shading. You want to be kind of neat, but you want to just be clear which side of the line is the solution. So what I'm trying to show here is if any point that you picked over on this side of the line, we would get an invalid inequality, and any point that we picked over on this side of the line would work. Okay? Sometimes you'll be graphing some one-variable inequalities, and we do it the same way. It's just your lines happen to be vertical or horizontal. So y is greater than -3. We will graph the line y is equal to -3, and this is going to be a dashed line. And let me try to color coordinate a little bit here. This will be purple, and so we will be shading this zone above that line. Okay. For the second equation, we'll do it in blue. X is less than or equal to 4.5. So we are just going to graph this vertical line at 4.5 and then shade everything to the left of that. Okay. So I didn't model plugging in the origin, plugging in 0, 0 to see if that point checks out or not. But if you have a horizontal line and or a vertical line, it's easiest just to look at the direction of the sign, a greater than or a less than sign. All right. And then the last thing we'll do for this video is to try to look at a graph and to try to determine an equation from that graph. So here we have a graph right here. It looks like we have a y-intercept. So I'm looking at the boundary line first. I don't care about the shading side yet. I'm just looking at the boundary line. Looks like we have a y-intercept of 1, and drawing a slope triangle, it looks like we have a slope of 2 over 1. So my boundary line is going to be the equation y equals 2x plus 1. And then it looks like it's a solid line. So we are going to be working with either y is less than or equal to 2x plus 1, or y is greater than or equal to 2x plus 1. Okay. Just because we are shading below the line, below and to the right of the line, I don't want you to always assume that that means it's going to be a less than symbol. In this case, it does work out that way, but sometimes things will get more complicated, especially if you have something maybe in standard form. I mean, what if you had 2x minus y is greater than or equal to -1. That's the same version of this right here, but here we have a greater than symbol. So I just want you to be careful with not assuming that just because the shading is below that we will always have a less than sign. I think it's good to check. So I'm going to hypothesize that this is my correct answer, this one right here. But let's plug in 0, 0 and test it. So is 0 less than or equal to 2 times 0 plus 1? It is. So that means that since we know that 0, 0 is in the shaded region, that means that this is going to be our correct final inequality. So y is less than or equal to 2x plus 1. Looks like we solved that guy, and that's a good place to stop right there.